All right, so the next talk is by Diane Salim on a data-driven approach for star formation parametrization.
Hi, everyone. Thanks for inviting me here. I'm a PhD student from Rutgers University, and I'll be talking about a data-driven approach to find equations for star formation parameterization. And I'm really interested in this because I'm really interested in what drives star formation in molecular clouds. And we know that stars form from gas, and we know this because we've seen some empirical scaling relations, such as that between the column density of gas and the column density of star formation rate. And we've seen these scaling relations such as that from all the way back from Kennecat 96 and further. So this plane is also known as the Kennecat plane. And we want to know how these scaling relations come about physically. So there are a couple of star formation models that we can analytically investigate. So one kind of model is called a top-down model. So equating some global properties of the galaxy. And for example, we have a model that equates the turbulence, momentum decay, and the feedback injection rate. This is the Forschungsjahr 13 model, which equates star formation rate to the column density of gas, velocity dispersion of gas, and the dynamical time. It has some correlation between these features. And I'll be testing a lot of these models on the Phi 2 galaxies. So I'll be showing this kind of contour plot on the Kennecat-Schmidt diagram a lot. And in all my plots, I'll be having the native Phi 2 galaxies in the gray contours at the back, and what the model predicts on the Kennecat-Schmidt plane on the green contours overlaid, and the dotted line is always going to be the original Kennecat 98 relation. And so this top-down model, I have like two metrics to gauge how well a model is doing. One is the R-squared value. So this model achieves R-squared value of 0.3. It's not like amazing, but another metric is how much dispersion is recovered in the Kennecat-Schmidt plane. So the dispersion is native to the physical processes, such as some stochastic properties in stochastic processes in the simulation. So it's physical. So this model achieves quite a good dispersion in agreement with native Phi 2 data. And so another category of models is the bottom-up model, where the physical relations of the small scales are summed up to get a relation on large scales. And we're interested in the properties of the gas like right next to the stars forming. And in this kind of model, we can say that there's a distribution of gas that has a log normal PDF shape, the width of which is determined by how much turbulence there is in the cloud of gas. And we can integrate from the critical density, where gravity takes over, to have some kind of turbulence regulated star formation rate law. And so this particular law was tested on a Higgs compact group galaxy, which is has extreme star formation properties due to it being in a group, and will be called the Salim A 2020 model. And it achieves a little bit of a better R-squared than the top-down model, but it does not recreate the distribution of the native Phi 2 galaxies very well. So can something like machine learning help us at all? So there's been a lot of advancements in the last couple of years with things such as regression models, one of which is called XGBoost, you might have heard of. It stands for extreme gradient boosting, as it is a distributed gradient boosted decision tree. On the user interface, it takes in pixel scale properties such as column density of gas, or velocity dispersion of gas, dynamical time in our case, and outputs pixel scale values, or corresponding pixel scale values for a target value variable. In our case, the column density of star formation rate. So it does really well. It does like better than all analytical models on an R-squared basis, and it also recreates the distribution on the Kenniker-Schmidt plane a lot better than all our analytical models too. So there are some pros and cons for this kind of model. It's highly optimized on a point-by-point basis. However, this mapping between the input variables and output variables is lost in how it works. So it's not easily interpretable and therefore not physically meaningful for us as physicists. However, it does really place a good limit on just how well any equation-based model can be, because it's not constrained to having to be expressed as an equation. So our goal in this study is to create a similar pipeline to input the physical properties and output some model for the target variable, but have it interpretable and equation-based, so we can look at it and try to compare it to analytic models that we might have. So the data we'll be using is the Phi2 data, and we'll be using the Latte suite, which features 7 galaxies, and we'll be using every pixel in every snapshot up to redshift 2. So the method that we'll be using to find our equation is called symbolic regression, and we're using a software package called PySA developed by Miles Kemnau. And in this algorithm, the equations are expressed as a graph, the nodes of which are the terms and operators in the equation. And it's a genetic algorithm, so in every step, a mutation occurs in which the node mutates to a different operator, say, or a branch is inserted, or some branches can switch over. And the complexity of an equation is the number of nodes in the graph. And so to test this pipeline, we created a synthetic Photosugar 13-like data set. We inputted these variables in this model with some injected noise. And here are some results for some of the found equations that we had. This is the one-to-one plot of the native Phi2 data and the result of the equation. And what was really interesting was that we found a functional form that exactly mimics the synthetic Photosugar 13 model. So that was really encouraging to see that this is an accurate way of finding parameterization for our target value variable. And so for our actual experiment, where we ran 2 separate experiments, one for timescales at 10 mega-year average star formation rate, which has more of the stochastic processes like supernova or radiative processes represented, and represented observationally by H alpha. And we also have a longer time scale at 100 mega-year average star formation rate, which represents a galaxy more in equilibrium and represented observationally by UV or SEV fitting. So here's some technicalities for the machine learning side. We used a total loss that was the sum of the mean square error loss and a quantile loss to try to incorporate the distribution of the data a little bit. And the top equations that we choose had to have a loss that is less than the best analytic models that we had. For the short time scale, it's the Salim 2020 model, and the long time scale is the Photosugar 13 model. And the R-squared for the found equations converged to the XGBoost R-squared, so that was also encouraging. And so here are some of the found equation examples. We saw that for the short timescale, a lot of the equations featured a linear correlation with column density of gas, as well as smaller contributions from the velocity dispersion of gas and the column density of stars, which represents the potential of the galaxy. However, it didn't recreate the dispersion in the Kennebec-Schmidt plane very well, like none of them. So we can't really, and the equations don't really seem like top-down or bottom-up, so we can't really say that much about it. But we are confident with some of our equations found for the longer time scales. The equations found look a little bit more like scaling relations, and it recreates the distribution of the native phi-2 data really well. And I like to highlight these pink lines, which are what the models look like when fiducial values for all the features besides column density of gas are inserted, and when we put them all on the same, all the found equations on the same Kennebec-Schmidt plane, we see that all the equations for the longer timescale experiment converge to the same line, whereas the equations found for the short timescale experiment have a little bit of scatter in it. So we can't say that we're super confident about that, but we are confident that we found the best equation possible at the longer timescale experiment. So the study achievement that this study's achievement has been that we've used symbolic regression to understand empirical and observational star formation rate scaling relations, which we apply to cosmological zoom-in simulation. And through that, we found some equations. And we've shown that the column density of gas, the velocity dispersion of gas, and the column density of stars, which is representative of the potential of the galaxy, is really important for describing star formation rate surface density. And for future works, we're thinking of applying this method to observational data like FANGs, but we have to be really considerate of the observational errors that might come with the data during training. We might input these found equations into semi-analytic models to see how they evolve and see if they come out similar to the simulation. And we want to explore architectural features to recover dispersion in the future state. So if you have any questions or want to apply this method, please. Thank you.
Okay, question?
Great talk. Yeah, it was a question about like one of these future applications, whether you were thinking about applying it also as a subgrid model for larger scale cosmological simulations like Galastris or Eagle, and in this case, whether you tried playing with the quantities, not like velocity dispersion, which will not be available in the simulations, but more like large scale, kiloparsec scale velocity fields.
Yeah, I think that would be interesting, and then interesting to see whether or not like large scale, or I'm also interested in applying it to more like small scale turbulent box like simulations, whether or not they have more agreement with like the analytic models more that are more suited towards that kind of data set. So I think the top-down models kind of emerge from this experiment because the 100 megayear timescale simulations are just like more in equilibria and more representative of what a top-down model might look like. Yeah, so that'd be.
Okay. One last question.
So for the 100 megayear time scale, the galaxy has time to move significantly during, over that interval. So did you use, so I imagine you might get different results if you used, if you took your star formation rate to be the average over the 100 megayears preceding, or say the average of 100 megayears around this instant, you might get different results if you sort of, wound the clock back to the start of the interval. Did you explore that dimension of, how to deal with the fact that you're looking at gas at an instant, but you're averaging star formation over a time when the galaxy looked very different?
No, we didn't
Just
investigate
something
that.
to think about.
Okay, yeah. Well, thank you so much for your comment.
Okay, let's thank Diana again.